Hey everyone, welcome back. In this short video, we're going to go through a demonstration of an InsightMaker model that implements Thomas Malthus's very pessimistic vision about the implications of exponential growth and the inevitability of exponential growth running into resource limitations and causing overshoot of populations that leads to famine and disease and pestilence and war. And this is what we're going to do today. And let's get started. Let's move into InsightMaker. All right, you should have a blank InsightMaker workspace in front of you. And let's build our basic exponential growth model. If you really want to, you can clone the model from Lab 1. This is basically the starting point of this model is exactly a replicate of what we did in Lab 1, in the InsightMaker portion of Lab 1, if you've gotten there. The first thing we're going to do is add a stock into our workspace, and we'll call the stock human population. All right, we can make it a little bigger. There we go, and we'll add a couple flows to it, because the stock can't change without flows. This is going to be an inflow that we're going to call births. And I'll just drag another flow out, and this I can keep as an outflow, and this is going to be deaths. And we're going to also add a couple per capita vital rates. So I'm going to represent these with variables. So this is going to be per capita births. And we'll add another variable that we'll call per capita deaths. All right. And of course, those variables, those per capita rates, will be linked using a link to the respective flows. So the births linked to the births and the deaths linked to deaths. And let's just add in our rate equations here that we need to determine the total number of births and deaths in the population. So the total births is equal to the human population times the per capita birth rate. And we'll hit apply. The total deaths is equal to the human population times the per capita death rate. And now we can start putting some numbers in the rates and in the initial stock, the initial human population. Let's make that start off at time 0 with 1,000 individuals. And the per capita birth rate, we're going to make 0.1. So basically, for every individual in the population each year, we expect 0.1 new offspring. Basically 10% of the individuals in the population will give birth to one offspring. We can think of it that way. All right. Per capita deaths, we will set at 0.01. That is 1% of the population will die each year. All right. So now we have an exponential growth model. It's basically, this is all we need to model exponential growth. Let's simulate it for 100 years. So I'm going to change this 20, which by default it always starts off at 20. I'll change that to 100 years for the simulation and hit simulate. And if we want to make it go faster, we can. And we can see that there's exponential growth. And I'll just configure it so we don't need to see the per capita births and deaths in our plot. We just need to see the human population over time. And we can see that after 100 years, we have about 6 million people. We started off with 1,000. So there we have it, exponential growth. Now, Malthus said that exponential growth can't go on forever. And that does seem like a fairly obvious point because exponential growth is pretty powerful. And, you know, if we wanted to run this model for even longer, say 1,000 years, we could. And I don't know if I even want to look at it, but now after 1,000 years, we have 3 times 10 to the 40th, or 40 zeros. I don't know how to name that number, but it's very big, and clearly we can't have that number of humans on the in the Earth. So, barring colonization of other planets, we will run into limits to growth, and that's what Thomas Malthus was saying. So, what we're going to do in this demo is to implement a limit to growth, and it's going to be a very severe limit. It's going to be if you exceed the limit. If we exceed the limit, then the population will undergo severe famine and the death rate will go to 99%. All right, so our normal per capita death rate is 1%. But if we exceed the limit, then we go to 99%. All right, so we're going to make a new limit. I'll make it a stock, and let's put it over here. You can put it wherever you want. This is just a suggestion. This demo don't feel like you have to replicate it exactly. We're going to create a stock, and it's called limit. This is kind of the limit, and above this limit, the population will crash. All right, and so let's set the limit just for the sake of this exercise. We'll set it at 500,000. So 500,000 individuals. If the human population exceeds that, they run out of food and the population crashes. Now, the first thing I need to do is connect this somehow to a vital rate. So what vital rate is the limit going to affect? It's going to be affected by the limit. Now, if the population exceeds a limit, the per capita death rate is going to go down to it's going to go up to 99%. So we're going to link the limit to the death rate, because the death rate is going to be affected if the population exceeds the limit. And we should also make a link from the human population to the death rate, because now the death rate is going to be a function of human population. If the human population is above the limit, then the death rate's 99%. If the human population here is below the limit, then the death rate is only 1%. All right. So that's the model we're going to implement. So clearly we have some work to do in this per capita death rate variable. So let's open the equation editor. Again, you click on the equal sign. If you hover over the variable here, you'll see an equal sign. That's the equation editor. And we can use the equation editor to do a lot of complex programming operations. And one very powerful programming operation that we're going to take advantage of in this demo is the conditional statement. That is the if-then-else statement. And the way that works is we ask a question. We ask, is this condition true or false? All right. And the condition is, does the population size exceed the limit? So if the condition is true, then the death rate is going to be 99%. If the condition is false, then the death rate is going to be 1%. Let's implement this. And we don't have to know, one of the nice things about InsightMaker is we don't have to know the syntax by heart. We can use this menu on the right-hand side of the equation editor to find what we need. And we can see that there's this if-then-else option that we have under the programming functions. And if we click on that, it'll automatically give us the syntax we need in order to write if-then-else statements or to implement conditional logic. So if a condition is true, then we do this. Otherwise, if the condition is this other condition, then we do this. And otherwise, if neither of these conditions is true, then we do this, and then we end the conditional statement. Now, we don't really need this nested if in here. We don't need to, all we need to do is ask, so we can delete that. All we need to do is ask if the population exceeds the limit, then we do this, otherwise we do this. So we can simplify this just a little bit, and now we can start to implement the conditional statement. And it's fairly simple to do this. All we have to do is say, and we can use these references to make sure we don't have any typos, we replace condition with an actual condition. So I can delete that and say now I'll replace that with human population above the limit. And when to test if something is greater than something else, we just use this caret or greater than symbol. And you should all know where to find that, hopefully, on your keyboard. And so then that's fairly simple. If human population is greater than the limit, or in this case, 500,000, then the death rate is going to be what? Should be 99% or fractional 0.99 of the population. Otherwise, if the population is less than or equal to the limit, we see that the death rate is 0.01. Should be like that. All right. This is computer programming, so some of you may need to take a few minutes just to wrap your head around this and make sure you understand how this works. But in plain English, it's fairly simple. If population exceeds the limit, famine. We have a severe disaster, 99% mortality. Otherwise, things are pretty good, and we have a 1% mortality. Let's hit apply. And now we should have a famine condition, and we should be able to see population overshoot. Let's see what it looks like. I'm going to put this back to, let's say, 200 years, and so we can see what happens over time. And here we go. So what we see is exponential growth happening up until the population reaches 500,000, and then the population abruptly crashes. And then it grows again, and it abruptly crashes, and so on and so forth. And it keeps on going and going ad infinitum. And we've now implemented Malthus's pessimistic vision about the future of human population growth. Now, before we finish the demo, I wanted to add one more aspect to this model, and that illustrates the difference between geometrical growth or exponential growth and linear or arithmetic growth. And so Malthus was saying the power of population is indefinitely greater than the power of the earth to produce subsistence. And so what he was saying was that the power of population is geometrical, it's exponential, and the growth of food resources and agriculture is only going to be linear growth. It's not going to be exponential. So let's just look at what that means, and we can actually quantify that and put it in our InsightMaker model. And so what we can do here, since the limit is a stock, we can change the stock over time in a linear manner, in an arithmetical manner, by adding a particular amount of potential for food resource growth, agricultural advancements over time. And we can do that by adding a flow in to this limit. And so we can, doesn't matter how we draw the flow, but we do have to make sure we can reverse this direction so it's an inflow, so that the limit is increasing over time, but it's increasing in a linear way. So if we just put a constant amount that is added to the limit every year, that is the number of humans that can be supported by the planet, we can make that number, say 500. We can support an additional 500 people every year based on agricultural advancements. So we start off at 500,000, but the next year we are at 500,500, right? And we just keep on going every year. The next year it's 501,000, right? And so we should see a linear increase in the limit, but a exponential increase in human population over time until it reaches the limit. And Malthus's point was that no matter what this rate is, if it's just an additive, arithmetical, linear increase, the power of the human population, the exponential growth, will always find a way to reach the limit, and we will have famine. It doesn't matter how fast this flow is. And we can test this now. So let's let's first try with a 500 increase in the limit every year and see what happens. So we should be able to just hit simulate and look at that. So we see that, yes, the limit is increasing over time, but the population is always able to pretty easily meet that or find that limit, and then of course it crashes. So what if if we change that flow to 5,000? So we have an even much greater increase in the agricultural production, and the limit to the human population is increasing dramatically every year. If we simulate it, it doesn't matter. It's the exponential growth is always going to find a way to reach that limit, and we can just keep on going and try, 50,000. And again, exponential growth finds a way to find the limit. And so just play around with this model. I think it's really a useful thing to be able to implement conditional logic. So make sure you understand how that works, and just play around with the model. If you want to add slider bars to the limit and try different, to the flow, that is the change in the limit, over time, you can do that. Just play around with it and make sure you understand it. And then once you do, answer the Top Hat questions on the Top Hat lecture page, and then we can move on to talking more about logistic growth and other models of limits to exponential growth.